Well, I think the moon's reputation for being barren is accurate by Earth standards, but not by planetary standards generally. I think it also helps that I happen to be a chemist, so I think in terms of what chemical elements are available. We can always make what we need from them, and of course all the elements are on the moon. The big resource that the moon has in terms of materials, of course, is the ubiquitous lunar soils. They're all over the place. For example, within a cubic meter of lunar soil, you have all the carbon, hydrogen, nitrogen, oxygen, and other constituents you need for a lunch for 2 people. You can make 2 full-size cheese sandwiches. You can have 2 12-ounce sodas. You don't even have to cheat and use sweetener. You have enough for real sugar. And you can have a couple of plums, and you'll still have everything but hydrogen left over. Everything that we want is there, it just isn't there in the forms that we're used to using here on Earth.
The challenge is to unlock the moon's resources. Haskin is developing extraction techniques. He chemically simulates a tiny drop of lunar soil. Electrodes are inserted. In a furnace heated to 2,600 degrees Fahrenheit, the sample is melted. Electricity flows between the electrodes and separates the soil's components. Iron and silicon will collect at one electrode. Bubbles of pure oxygen are released and will collect at the other. This basic experiment shows that simple principles can be applied to retrieve valuable resources on the moon. The production of oxygen could become a lunar colony's key industry, providing both life support and propellant for transportation. Metals derived on the moon could be used for manufacturing and repair of support systems. There are riches to be mined in the lunar soil, but the technology to do so must first be developed on Earth. That's the hitch. Nearly half a ton of rocks and soil were returned from the moon. It is treated as the rarest, most precious material on Earth. NASA distributes only minute amounts to researchers. All common elements exist on the moon, but some have combined into minerals unknown on the Earth. Lunar soil contains a high proportion of glass, formed when meteorite impacts melted the surface. The tiny beads can make the ground slippery, as the astronauts found out.
Further down. Oh, there you go. Uh-oh. Ah, rat. Okay, up, here we go again. Give me a help.
They say give it a slight rotation clockwise as we're lifting out.
Okay. Stay there. Stay there.
To design equipment to process lunar soil by the ton, to test a hunch that moon dust can be turned into concrete or a fertile plant-growing medium, how could anyone succeed, limited to a thimbleful of the real stuff? The answer may be in our own backyard, in a deserted quarry near Duluth, Minnesota. Geologist Paul Weiblen studied the first Apollo samples in 1969. Years later, he was struck by their chemical similarity to these rocks. They're the closest terrestrial match to moon rocks yet identified. To come up with a reasonable substitute for the powdery lunar soil, Weiblen had to take matters into his own hands. In the course of an afternoon, he accomplishes what took 3 billion years of meteorite showers on the moon. Equipment once used to process iron ore pulverizes the rocks. To simulate the intense heat of an impact, the soil is run through a plasma reactor at temperatures up to 5,000 degrees Fahrenheit. The end result is called Minnesota Lunar Simulant, or MLS. It's not a perfect match of lunar soil, But its similar bulk chemistry, mineralogy and microscopic beads of glass make MLS an important research tool.
I'm particularly interested in this work on simulants because it provides a way of doing studies now that will enable future people on the moon to use the lunar materials for plant growth, to recover oxygen, with all the mistakes having been made first on Earth.
Minnesota Lunar Simulant is available to researchers by the kilogram for a nominal fee. As interest grows in developing lunar industries, orders have come in from around the world. At Shimizu Corporation, engineers use MLS to experiment with lunar concrete. Every pound of supplies launched from Earth costs something near its weight in gold. Learning to build with local materials will be the only viable solution for construction on the moon. Stress tests show the simulated lunar concrete to be at least as strong as the terrestrial variety. But making concrete on the moon will require the development of another resource, lunar water. At the University of North Dakota, researchers have devised a way to get water out of rock. They heat lunar soil simulant to 1,600 degrees Fahrenheit, then introduce hydrogen into the system. As the gas flows through the soil, oxygen is released to combine with the hydrogen. The resulting steam condenses into water. Processing lunar soil may look easy, but it means generating high levels of electricity and heat on the moon. At McDonnell Douglas Space Systems Company in California, engineers have found an innovative solution. They routinely melt lunar soil simulant in a graphite mold at over 2,000 degrees Fahrenheit, but they use no electric furnace. They harness the oldest source of energy around. In the 1980s, McDonnell Douglas developed massive solar concentrators as part of a program on alternative energy. Today, these seem a promising technology for the moon. The mold is mounted in the center of the concentrator. Sunlight is focused on it. In only 20 minutes, the soil inside reaches 2,200 degrees and melts. On the moon, where there is no atmosphere, the sun is even more powerful. The mold is left to cool overnight. 24 hours later, it is still warm to the touch. The experiment produces a tough, ceramic-like material that is nearly twice as strong as concrete. Someday, materials like these could be used to build habitats or to pave the roads to lunar cities. There is gold in those hills, perhaps enough to sustain a lunar colony.